Hello everyone. In this video, we will be discussing some problems based on the impact load. Already in video 1 and video 2, we discussed the introduction, what is impact load, what is impact stress, what is impact deflection. All those things we discussed, even the derivation also we discussed, what is the formula we will be using to find out all the requirements based on the impact load. So in this video, two numericals we will be discussing, and in detail we will discuss. I suggest all the students to solve the problem after watching this video. Just take down only the inputs of the problem, and you will be knowing what is the formula to solve the problem. And I request all the students to solve the problem on your own, and later you can cross verify your answers with the PPT video. So we shall discuss the very first problem. An axial pull of 50 kilonewton is suddenly applied to a steel bar 2 meter long and 1000 square in cross section. If modulus of elasticity of steel is 200 kilonewton per meter square square, find the maximum instantaneous stress. Second one, maximum instantaneous extension. Third one, strain energy, and fourth one, modulus of resilience. You can able to see this particular problem. The very first line we can understand impact load based on the axial pull. So along the rod, the load is falling. So what is the amount of load is falling on particular rod collar is 50 kilonewton, and it is suddenly up to a steel bar of 2 meter long. So there is here a vertical rod of length 2 meter, where assume that this and it is fixed, obviously supposed to be fixed because that is a condition of the impact load problems we discussed. So it is fixed here, and this is the 2 meter rod, and the cross section they have mentioned is 1000 square. That is fine. Mostly it is having circular cross section only, and 50 kilonewton load is applied. You can able to see there is a load. Assume that this is a particular point. This is a particular point where the load is fixed initially, and suddenly this load is allowed to fall on the collar, where in the bottom will be having the collar. So if this 50 into 10 power 3 Newton load is falling, they have not mentioned what is the height. So we will be finding out, and they mention the modulus of elasticity, that is the Young's modulus value is given. So all these four things we will be finding out. So let me write down the given data. So the load given is 50 kilonewton, so 50 into 10 power 3 Newton, and the area is 1000 square, and the length of the rod is 2 meters. So let me write that in unit, so 2000 and Young's modulus is 200 kilonewton per meter square. Again, let me write that in Newton per square. So the unit become, I mean, the value becomes 200 into 10 power 3 Newton per square. First, maximum instantaneous stress. So what is the formula to find out maximum instantaneous stress? Means 2p by a. Just now we discussed. If the falling height value is not given, only the sudden load, means directly we can use this formula. So let me substitute. The p value is 15 to 10 power 3, and area is 1000. So after the simplification, the maximum instantaneous stress value is the 100 Newton per square value. Others, you can directly use the formula, the final formula, where you can substitute the h as 0, since the falling height value is not given. And moving to the second case, maximum instantaneous extension. So that is the delta L value we need to find out. For that, we should be knowing the Hooke's law formula, because this is the only way to find out this the outcome, that is instantaneous extension delta L. So let me rewrite this Hooke's law in this way, that is strain is equal to stress divided by Young's modulus, where the stress value just now I calculated, that is the instantaneous stress value, that is 100, and Young's modulus it is 200 into 10 power 3, which is given already in the question itself. So the strain is nothing but 5 into 10 power minus 4, since it is a unitless. Let me write the strain without unit, and we know what is again strain, which is nothing but a change in dimension to the original dimension. So change in dimension thing, but because of the impact axial load, what is the change which is happening on the particular bar, and it is nothing but the length of the bar. So let me write the delta L on the left side and other things on the other side, since we are looking for this one. Now the Young's modulus value, that is the strain value, is nothing but 5 into 10 power minus 4, and the length of the rod is 2000. So after simplification, I'll be getting the instantaneous extension. Now that is the sudden load deformation value as 1 mm. Moving to the third case, what is maximum instantaneous stress? Sorry, the third one, strain energy. Strain energy is denoted as U. So formula already we discussed, and the derivation also we see in video 2. Have a look on that one. The formula to find out strain energy is nothing but sigma square divided by 2e into v. Here what does the v means? The volume. The volume can be found out by using the area of cross section into uh, what is that, the length of the rod. So the length of the rod is 2000 and the area is 1000. So we know what is the impact stress and even Young's modulus value. Substitute in this thing, and volume you should be knowing, it's always the area of cross section into the length. So after the simplification, we are getting the strain energy as 50,000 Newton mm. Strain energy unit is Newton mm. In case if you substituting the data either stress or Young's modulus and volume in Newton mm, final answer will be in terms of Newton mm. And the fourth one is the modulus of resilience, which is denoted as mu suffix small m. The formula for modulus of resilience is sigma square divided by 2e. We know sigma value, we know e value. Substitute in this formula, and after the simplification, we are getting the modulus of resilience as 0.025 Newton mm divided by mm cube. Even you can cancel this also. So Newton per mm square will be the modulus of resilience. So this is how we need to solve this problem. Moving to the second problem, the same category, we'll see how to solve this problem. So the given question is a 1500 mm long wire of 25 mm square cross-sectional area is hanged vertically. It receives a sliding collar of 100 Newton weight and stopper at bottom end. The collar is allowed to pull on stopper through 200 mm height. Determine the instantaneous stress induced in the wire and corresponding elongation. Also determine the strain energy stored in the wire. Take modulus of elasticity of wire as 200 gigapascal. So this is a very similar, outcome of the previous problem. So let me write down the given data. So the load is 100 Newton and area of cross section directly given as 25 mm square. And length of the wire is 1500 mm. And height, falling height is 200 mm, and Young's modulus is 200 into 10 power 3 giga to the gigapascal to the Newton per mm square. So the conversion is into 10 power 3 Newton per mm square. And let me go with the direct formula, since the falling height and all other things given. If you, for your info, for your reference, you can draw the sketch. You can able to see area value, the length value, the load value, and the falling height value, and even the collar or the stopper. Everything is shown pictorially, so that it will be easy for us to find out what kind of load it is. Again, it is an axial load, since the load is falling along the rod axis. So the formula is sigma impact stress is equal to P by A plus square root of P square by A square plus 2 EPH divided by AL. So I know all the values, load I know, area I know, falling height I know, length I know. So if I substitute everything in this equation, and finally I'll be getting sigma impact stress values 465.89 Newton per mm square. So this is how we need to solve the first one. And second one, in the instantaneous deflection, so that is stress into length divided by the Young's modulus. Again I know all the values, so after substituting in the formula, I'll be getting the deflection value is 3.49 mm. And strain energy, the formula, same formula, sigma square by 2e into volume. So again the volume is nothing but the length into the area of cross section. So after the substitution in the formula, in this given formula, and finally the strain energy we will be getting as 20,348.76 Newton mm. So this is the output for this particular problem. I request everyone to solve this problem by using your own calculators, and just do change the values of area, Young's modulus, length, and other things, and just find out whether you people are getting the similar kind of answers. Thank you.